it's also interesting to see that the title looks like an abstract nowadays. Okay, and not only did he propose that these stars would exist, but in fact, the purpose of the paper is to actually.
So now in this set of slides, we will discuss a bit about dust and cosmic rays in the interstellar medium, because this will be also important. I will spend some time on physics of dust grains and cosmic rays, so whatever cosmic rays can do, etc. This part will come from this book called Bruce Drain, and it's again it's available in electronic form.
And of course,
and I will also do a little bit from
live surface of this planet.
So I'm sorry, it's not visible. So physics and chemistry of interstellar medium by.
It's not like what we think of as a dark star.
Okay, so the first thing we want to ask is dust grains. So how do you form dust grains, and where dust grain can be formed? So this is our first exercise. In the diffuse interstellar medium, you know the densities can be anywhere between 10 to 100 particles per centimeter cube. And abundances, if you look at the table I showed you a couple of lectures back, a carbon, so for every 1,000 hydrogen atom, you may have, or few thousand hydrogen atom, you will have one carbon atom. It's few times 10 to the minus 4 is the ratio. So if you say I'm going to form grains, for example, I'm going to form graphites, you are going to mix carbon and hydrogen, right? That's how you'll form them. So you see that it is going to be very, very less probable of meeting one of them together. So the way we will emphasize this need is that, suppose you imagine that I want to grow, and what we know from interstellar medium observations is that the grains have all sorts of sizes, right? Grains can go from smallest micron size to some few millimeter size, right? So everything you see, for example, the stone which is going in around interplanetary region, we will call it as dust particle. So the basic idea we wanted to know how to form dust particle. The simplest way to do is that you will say that what is known as attachment, collisions followed by sticking, right? So imagine I have started with a particle of size A, and I just say that another particle comes and sticks to this particle, and then it sticks like this, and you can imagine for the simplicity, we assume that you can now make it to an equivalent sphere with a higher mass, right? So they grow. Suppose imagine that the sphere grows by sticking. Then one can ask the question, how much time it requires for me to grow a mass of dust grain md. So we can write down dm by dt. dmd by dt will be proportional to, you will say that okay, this is proportional to the probability that I have you can think of like a seed or a core, probability that some particle of size A will join me to the core. So basically you can start with, in the beginning the area will be pi a square. Okay, so I have some stupid thing I have done, A and R, because they are same, that's why I put here. So start with, let's take A be the size of the grain. What is the probability that they will be sticking to each other? This will be depending upon area and sigma b, right? That's what you will do. So the sigma will be like pi a square. You have to weight it by some parameter which is related to the sticking, for example, how often it can stick. So one is the physical area multiplied by the correction factor, like what we have been doing before. V into n will give me the rate of collisions, and if I put the mass of individual particle, I can say that mass, the rate of increase of mass. Right? Every time the collision increases the mass by m, then this is what it is, and I can just write down ma and na in terms of density. Given the background particle density, dm by dt will be like this, proportional to like this, and this coefficient will depend upon the property of the grain. If you physically collide, will you what probability that it will stick and stick forever? Okay. We can also write down this as in the framework of the dust grain, it will be like 4 pi r square. Rho d is the density of dust grain, and dr by dt, because actually I should have written this as 4 pi a square, rho d dA by dt. So these are the two equations I can set up. Right? I can say that I can calculate the increase in mass by saying that how often collision occur, each collision increases the mass by 1. Or I say that I will just say that if I make an assumption that every collision is going to make this dust grain going to a spherical thing immediately instantaneously, then how will I know dm by dt? I can say that it is, I can relate it to the change in the radius of the dust grain itself. So if you equate these two things, I can write down the expression for dr by dt, which will be proportional to what is the kind of velocity of this particle which are moving around, dust particle, which will be related to the temperature of the gas, density of this dust particle in the free medium, this coefficient, okay, are divided by 4 times the density of the dust grain. So which means that if I'm thinking of carbonaceous dust grain of particular density, blah 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 blah. So if you plug in the typical values one has, so it will be of the order of q into 10 to the minus 13 centimeter per year. It is completely clear that it takes huge amount of time. To grow a particle to a centimeter, you will require something like 10 to the 13 years. It's impossible, right? So you want to make a micron, you are talking about nearly close to the age of the universe. So this is the big bit of the problem. Here I have used the density corresponding to this, and average mass I have taken weighted by whatever is the metallicity of the gas, and this coefficient given by so the rho density I have taken. So I think this is just an indicative number. This tells you that if you are forming dust grains, you are not going to form dust grain in the standard interstellar medium. In fact, this would have been much shorter time scale if my rho A was much higher than what I see in the interstellar medium. So where in the if you look at in the interstellar medium or in our galaxy where the densities are higher, you will say the densities are higher in the molecular region. The enhancement will be of the order of 100 times the mean density or 1,000 times the mean density. Whereas if you go to the star, you go several orders of magnitude. I think this is the ratio grams to 1 gram per cc is the density, the 1 particle per density in the higher sun. So you are talking about this gram mass, that is the ratio, 10 to the several times, several orders of magnitude gain you will get if you go to the stars. But the stars are too hot. Right? So what happens is that if you go to a low mass star where the outer photosphere is much less hotter, so you go to a star of 2000 Kelvin or star of 200 Kelvin surface temperature. This is very low mass cold stars. Then it is possible that in the surface of the stars, this reaction will take place in a much shorter time. First of all, you have metals. So I'm going to stars will have more metals to hydrogen atom compared to the interstellar medium itself. Right? Means like or equivalently, they will have same number or more. Diffusion is there, they are more. Otherwise, they will have the same number like interstellar medium. And their rate will be higher because the densities are several orders. So you can easily form dust grains in the photosphere of Earth. Then you will ask me, what will I do? I want dust grains in the interstellar medium. What will I do with forming dust grains in the photosphere of stars? Then what happens is that these dust grains, when they start growing, they have sufficient area. When they have sufficient area, they will start absorbing the photons which are coming from the interior part of the star. So they will have a drag which will drive them out, like, exactly like the way you see cometary tails and all, right? This is radiation drag, or you will call radiation pressure. Radiation pressure will drive them out. So simple way people thought of producing dust grains, one of the ways. Okay, so basically you remember dust grain production will happen when the densities are very large, so that you can produce them. So in a compressed region, dust can be produced. Wherever you end up compressing them in the shocks or whatever, they have higher probability of producing dust grains compared to the normal interstellar medium. So this is one of the things one is talking about. But destruction of dust grain can happen through various processes, right? Direct heating of radiation field. If you heat something, it can get hot and it can melt or it can evaporate. So you will lose the grains by. You can also lose grains by whatever you call shocks or anything suddenly heats up and completely destroys these grains. So we will again grain formation and destruction has to be done in a more careful way. And this is the first step you have to do before you form molecules. Right? Because molecule we say molecule will form on top of dust grains. So there are sequence of equilibria one has to worry about.
But of course, if
when you go
photons,
from
this
dust grains
motion and
to
this property also
other,
high frequency
other molecules and
gravitons,
higher things.
so to
Okay.
say. But in fact, we like to
The
think
importance of this equation,
nowadays
whatever I have written
about the
down, is just to
dynamics of
tell you
black holes,
that
the late-time
it's
dynamics,
difficult
they're
to form
all
dust grains in the free
contained
space.
in this
So
line.
this
Why
makes
do we
us
governs
even more
how black holes will form
worried about how are we going to form life, because life means you have to form more.
Finally,
you have to bring in
if
more
you start
molecules
moving
which are
inwards
much
and
closer
what
to
we're spinning,
so it is very interesting. That is why one is talking about
an ergoregion. This is a region where things
protostellar
have
disks.
to
When you
rotate
form
a lot.
stars, before
Okay?
forming stars, you
So
may
if you
compress the gas with a
construct
much
a very
larger
powerful
density,
spaceship
and also you
and
may
try to
be,
study a black
because of
hole,
angular momentum, not only you will have
always
star,
free
you
to
will
turn
also
the
have
engines on
some kind
here,
of high density
and we may
plate,
address
which may end up
with
as
respect to distant
stones and
stars.
whatever we call
Okay?
planets or
Once you're in the
interplanetary debris
ergoregion, once
or
you're
whatever it is.
here,
So this physics is
you know,
very,
it doesn't
very,
matter
very
how
new,
powerful
and
your
it is
engine is,
gaining
it doesn't matter
momentum
how
now, because
developed you
now
are, you
bigger
will
telescopes will
always
allow you
rotate
to
a lot.
directly image
When
regions of
Roger
star
Penrose
formation
noticed
and to
this,
see
he
like
realized
whether you have high
immediately
density
that this is a wonderful
do you have
mechanism
this
to
kind of
extract
dust
energy
particles,
away from black holes.
higher mass
I construct the
molecular
device, it looks like it's
gas
a
which
primitive
are there or
version
not. So this
of any
is
device that
not done very much
civilization
in
could
detail
build.
in the
I
past,
could
but now it
construct
is
this
gaining
stuff
momentum, and
in
you
a
will
little
see a
ring
lot of people
where
working
it
in
fits inside the
issues
ergoregion.
related to
I
planet
lower this
formation,
device, it sits
protoplanetary
attached
disks,
to a
right?
magnet.
And
Okay?
life at all,
Because it sits in the
life and
ergoregion,
complex
it has to
molecules.
co-rotate.
This is very interesting topic.
So this
Unfortunately,
magnet
very
then
few
creates a
people
very flux
represent it in
in
our country.
this
Yeah.
circuit, and then
So
Faraday
if
inducts them all down to those
this dust grains
lamps.
can be
which we
formed in
got. Okay?
protoplanetary disks
Of
in
course, they try to
star-forming
not
regions,
at the
then why do
expense
people
of
think
the
that
black hole.
they are formed in atmosphere of late-type
It's very
stars?
simple, and people usually tell
See,
me, I don't see anything
we are
special
also
about that.
seeing them.
I can construct
We are also
exactly the
seeing
same
them
device,
everywhere, right? So
place on top of
it's
the
not
Earth,
just
and it's
planetary
do exactly the
system.
same.
We are
I
also
believe in
seeing in
ergoregion.
diffuse interstellar medium. How do you
It's
understand
very fun.
matter in diffuse interstellar
The
medium?
difference, of
I think this is
course,
where
is that
this formation
you're
method people have
receiving
seen
the
around.
ring
Suppose
in
if you
nothing.
go around
Okay?
cold
You're
stars,
placing this
you do see
apparatus
dust
in vacuum.
enhancement
So
of
you're
dust
actually extracting
around
energy
them.
away from
So
vacuum.
that's why people feel
It's not sitting
there is proof
on
for
any
all of them,
matter
right?
structure.
But which process
Very
will
good.
lead to
Now,
volume
okay, we know all
filling?
these nice properties about black holes.
That is
How
the
do we
question number.
go
For
to
example,
test it?
if you think of
Now we need the black hole to
biological molecule
interact
and
with
all,
us
you would
in some
that is
way or
why you would
another.
prefer them to be around
And I
evolved
think by
stellar
now,
system
since we're celebrating the
with the
decade of
planetary
gravitational astronomy, we
planets
know
around
that it
them.
does.
So
By
what I
only
meant by
gravitational waves.
molecule or what I meant by dust, I'm using
The
them
first
equivalently, right?
thing that gravitational
So
waves should
some dust
exist was
particle which we
done
are
by
seeing
Einstein
in
in the same
interstellar
way
medium.
that we do in class. Every year when we want to understand sound waves, we just linearize pressure and density in this room. For example, we linearize the fluid equations to arrive at something that looks like a wave direction with some velocity. Okay? When Einstein did this for the geometry, he found exactly the same thing, except that space-time gravitational waves seem to be propagated at the speed of light. Okay? Well, there's actually some components which travel at whatever velocity you want. They're pure gauge, but it took us a lot of decades to understand what that even means. Okay? Well, we became very good at understanding what that means. We actually spent a few decades building devices to match these waves. And after roughly 100 years, we built a device that actually catches them. I think it's also interesting here. Let me just pause. When Maxwell predicted waves, it took roughly 12 years to go to the lab and check that the prediction of electromagnetic waves actually correspond to light. Okay, so we're getting to a stage where decades turn into centuries, and it's useful to keep this in mind when we think about tests of Einstein's theory. There's a lot that went into this discovery, so it's very easy for any of us to be speaking about gravitational wave revolution and neglect the fact that we have to have astrophysics under control, what's the number of sources, how many binary systems are actually coalescing. We need to understand black hole physics. We need to understand how we simulate black holes in the computer. We need to know what type of framing for numerical relativity we need to evolve these guys. Of course, we need to build the instrument. We need to understand the partial differential equations. if they are composed by Einstein's equations, even well composed, they know how to take initial data and evolve it in a predictable way. Quantum mechanics that now goes into detectors and so on and so on and so forth. I'm not going to talk about all of these, but let me just point out that the signal we expected looked like this. These black solid lines on each of these are true of the detectors. The output, the noisy output that was actually coming from the detector was this. And you see that even nowadays, it doesn't look that much different. This is the challenge that we're still being given, and I think this is useful for theorists like me to have in mind when you actually try to constrain the theory. The way we have to go around the fact that noise is just too large is not too complicated, but I think we should know it. The idea is to filter the output of a detector. So you just say you take some source, it's emitting gravitational waves, okay? It reaches your noise detector and has some output f of t. And the idea is fairly simple. You filter the output, some filter that you need to come up with, until you have some nice plain signal x. Okay? So if you decompose your response f of t into the signal you're looking for, plus some random, assuming it's stationary noise, okay, the idea is to build the filter in a way that you maximize the signal-to-noise ratio of your filters. And you can show that for stationary Gaussian noise, in fact, the filter that's going to maximize this is called the Kalman or Wiener filter. It's the match filter. You need to build a filter that corresponds exactly, well, in the frequency domain to what you're looking for. This is important because it tells you you need to know what you're looking for. If you want to do the best possible job, you need to actually know what you're looking for. It's not enough to think, to hang your mind and say there's some gravitational wave out there. Okay? It looks like something like this is a MATLAB example, I think, a few weeks ago. Okay? Assume your signal is weird and looks like this, but in fact, the noisy output looks like this. So what you're going to do is filter the output with a match filter, which is this guy or something very close to this guy. Filtering means just cross-correlating, doing an integral. Okay, so you're sweeping the filter across the output, and the result of that cross-correlation is shown here. The signal-to-noise ratio as a function of the sweep time. Okay, and it's also kind of very clear to see that when the filter picks up the signal, you see a peak in your signal-to-noise ratio. That's roughly the idea. Okay, and this means that we need to know how a pair of black holes look like in this framework. Okay, we need to take two black holes, merge them, and find the gravitational signal such that we can filter the output of our detectors. Okay. Now, of course, you're going to ask, okay, that's beautiful, but is it a 1 solar mass black hole against a 10 solar mass? And I'll tell you, I have no idea. The universe could give us whatever, right? So we need to be a bit heavy on this. We need to actually use a large number of templates that somehow capture all possibilities that were out there for us. Okay, based on some priors, and we're going to go there in a moment. Based on what we understand about our universe, we don't expect black holes of very small mass. We don't expect black holes of gigantic mass. Okay, even though surprising appear. But this is the idea, and it worked. 10 years ago, we actually saw the first gravitational wave event. I wish it was like this, maybe not. I don't think that has. Okay. And here's a few of them. There's something I'm reading. The scale of mass. We've seen them in all sciences. Okay. We've seen surprises in astrophysics. Some things we predict well. Black holes of large mass. Some of them should just not exist there. We think that very massive stars should be unstable. Okay. We don't understand if some of these guys are actually evolving in vacuum, whether they're evolving close to accretion disks. But I'm not going to focus on astrophysics. I'm going to focus on fundamental issues. Okay. This means I would like to take all the events or one of the events and test general. Okay. And by tests, I mean, well, first of all, how do I determine masses and spins of these objects? Okay. Is there lateral radiation? Are these guys carrying, I don't know, electromagnetic charge? Everything in our Earth is charged. Are what? It's actually the theory that's merging these compact objects, general relativity, or can we find evidence that something there is acting when gravity is really strong in dynamic? How do we do this? And actually, these guys will probably not evolve in vacuum. Vacuum is a very ideal notion. We're not in vacuum here. It's very unlikely that black holes will ever see vacuum. How do we go around and test this? And in fact, you can use the early stage, the slow motion stage, to test most of this. As you know, how the frequency increases and the amplitude increases through time. It's relatively straightforward to estimate individual masses and spin. It's also more or less straightforward to constrain at least the dipolar moment of these objects. You can use the final stage through spectroscopy. You can use the fact that these black holes are really down like a bell to do physics, and I'm going to go there in a moment. And you can even ask another question. How do I know that I'm looking at black holes? How exactly, this is a question, by the way, that my family is always asking. How do you know it's a black hole if black holes are black? How do we do this? How do we go beyond the statement that, well, they should just be very complex? And they look dark. I haven't seen that. It's a very, very important state of affairs when you have high quality data to work with. Let me talk to you a little bit about quantum censorship, whether or not when I align these guys, there's still going to be an horizon covering the singularity that you have in the interior. I think this is a very intellectually stimulating discussion because I told you that quantum spin, okay? When you plug the speed of light and Newton's constant back, you're going to find that the one black holes only if this bound is satisfied, okay? A over n in those units have to be smaller than 1. If you plug the numbers back, they look like this, okay? It's something. But if you calculate the left-hand side for the sun, it's over the 1.01, given the uncertainties in the rotation of the sun. If you calculate it for the Earth, it's over the 10 to the cubed. And if you take your little brother or sister and ask him to take a spinning top right there on the floor, well, you can see how much it is, no? C is 10 to the 8, G is 10 to the minus 11. So your little ceiling will produce something that's spinning with 10 to the 18 or so. Okay? So, of course, we should worry. At least according to this way of quantifying the rotation of a black hole, the spinning really slow. So, I'm going to do the following thought experiment, which is I'm going to throw stuff at black holes, but I'm going to throw them in a way that there's just too much angular momentum. I'm going to throw two black holes at each other, and I'm going to place too much angular momentum in space-time in a way that this is violated. Okay? That means that if the objects merge, they collide and merge, and form a single thing, it could not be a black hole. There's just too much angular. Okay? If nothing else happens. So here's my simulation. The colors are gravitational wave amplitude. They're going to try to merge, but if something happens, they know something nasty is going to occur. So they do one orbit around each other, then they zoom out, they do two orbits around each other, they release all the excess angular momentum, and then they merge. Okay? This is a typical example of what happens when you try to destroy black holes. The field equations don't allow you to. We don't really know what's going on. We don't actually even have a proof this is generic. Certainly, when you give up 4 dimensions, it doesn't happen. we know of examples in higher dimensions where we do destroy black holes, but we seem to be safe in our little universe, four-dimensional universe. It's one of the interesting things that happens, or that may happen. Okay, so I'm going to assume, given all the decades of efforts are trying to destroy black holes did not work, I'm going to assume black holes are out there. Okay, and I'm going to try to test now whether or not they belong to the curve family. There's a few different ways of doing this. I'm going to use the black hole itself. I'm going to use what's called black hole spectroscopy. And this means the following. I try to convince you, well, it's a theorem, that if your universe is vacuum and stationary, then the final state, this guy over here, should belong to the curve family, to Brown. Okay? If you go backwards in time, well, it's certainly not stationary, and it should be a slightly disturbed black hole, some wiggly thing. Okay. Well, so you could think, let me expand that wiggly thing around a curve line, right? Because if you go backwards in time, certainly at some point there would be the curve line plus something small, right? It's exactly what you do when one understands sound waves here, except that now instead of a constant pressure and density, you expand around the curve line. You will find that there are fluctuations, the little wiggly things. You put them in Einstein equations, you drop all the second order quantities and higher order stuff, and you end up with a first order quantity that obeys this very simple partial differential equation. Okay? In fact, this master function psi is describing a certain combination of volumetric fluctuations. Okay, all the geometry is in that side. There's an effective potential T. It vanishes at the horizon at infinity, and there's a structure close to the line ring of all the bases. Okay, so you're basically following the Schrödinger line equation. And the way we have to solve the Schrödinger equation is, well, we usually do an harmonic decomposition if the states are stationary. Okay, and we find the characteristic energy, the eigen energy, if you want, the eigen frequencies of your system in that way. Now, what does it mean to calculate these eigen frequencies? Well, it means to impose correct boundary conditions and solve the differential equation. Okay, you can imagine that if you try to do this for black holes, they shouldn't really be allowed to be real, these numbers, because the black holes are dissipating stuff. Energy can enter the horizon, energy can dissipate away to infinity, right? So you'd expect that you're going to find numbers that lie in the complex plane. And you do find that. These numbers have a real complex component, okay? We know them to 20 decimal places of accuracy. You can find tables in my webpage, and there's a handful of other groups with the same numbers, okay? We know them really well. Now, we do this doing a Fourier transform, but we're interested in the time domain. Okay, so if you think about inverting the interval frequency, you usually use quantum integration, where these numbers are just poles of the Green's function, and therefore they contribute a sum that looks like this. Okay, the imaginary component sits here, it gives you an exponential time decay, and the real part gives you some oscillation. Okay. Good. So the most important number of this calculation is what we call the fundamental mode, the most dominant mode in gravitational physics. It looks like this: 1 kilohertz for a 10 solar mass black hole, and roughly 0.5 milliseconds for a black hole. Okay. So that means if you take Pune, which is roughly the size of this guy over here, the signal, the disturbance, would then about something of the order of 0.5 milliseconds across Pune. Okay? Of course, the reason is things are traveling at the speed of light, okay? Not at the speed of traffic. Yes. Okay, now I want to test the theory and let me tell you what exactly I mean by this, okay? If you have a string, so you do an example set calculation, you calculate the frequencies. They look like this. If the string has fixed ends, it's a 30-second calculation. And that means that if you actually measure a mode, okay, so you measure n equals 1, you know it's n equals 1, you know the frequency, you can invert and find the length of your string. But if you happen to measure any other node, well, you can repeat calculation, right? And if the length agrees with the current node, fine. If it doesn't agree, I don't think it can be a string, which makes sense, okay? So in general relativity, we do exactly the same. One mode now has two components, real and imaginary. You use them to calculate mass and spin of a black hole. If you add them, well, you say either mass and spin agree, or Einstein was wrong. Okay, that's more or less the idea. Now, this is easily said. This is done for the sun for decades. We know the sun really well. The problem with black holes is the sun over here. They don't really ring. Okay, the quality factor of a black hole is over the 3. And this is the source of all the problems we've been having. Okay. But we can do it. And this has been done. Let me quickly go through the first spectroscopy result.
So the previous equations, so the IUCAA, we can estimate that. So that universal constants.
F times tau.
Yeah, like you see,
Yeah.
everything cancels out. It's like 1.3 times 0.5. So that it's like a universal constant.
Not really, because this is for non-spinning black holes. I'm assuming here the black hole is non-spinning. If it is spinning, so all this plot is for a non-spinning black hole. If it's actually spinning, that number will go very slightly up. The quality factor goes up to, instead of 3, roughly 5. If the black hole is spinning at 90%, the stuff we expect to find out there, up to quality factors of 5. It doesn't vary much, but it does vary a little.
Okay. So which means that suppose we have like at some point we can measure the count of many like cases. And we can average them. So if Einstein's theory is correct, then we should kind of like expect a single number. Is that
I think that's correct. And you don't even need to average out a number because we know this distribution as a function of spin. We even know the fine details, so we can stack the events appropriately. And I think this has started to be done within last year or so. But we're still in kind of an infancy. The signal to noise ratio is still rather small, but that's exactly the idea. I think that's where we're going in the future. In fact, well, I was saying that the quality factor being low is responsible for something that doesn't look quite exciting. Okay, this is the first test. But let me explain why I think it's very exciting. I'm showing you here the decay time. Yes.
You have enough simple to noise ratio in the ring down. I mean, measure the spin from the masses.
Very poorly. Very poorly. So
How would you know?
yeah, very poorly. So in the first event, which is still the loudest, in the first event we've seen the signal to noise ratio in ring down is of order 7. Okay, so it's marginal detection. It's marginal threshold. So we can do a job, but as you see here, it's not so good. Okay, and what you see here is what we can estimate from this spectroscopy analysis. What we do is the following: we first take the full signal, this full signal, and we find the best fitting numerical simulation here. Okay, best fitting means we play with the mass and spin of the individual components. We find the final black hole in the simulation, and from that we estimate. Well, we have mass and spin. We calculate frequencies. The black solid line is the 90% posterior for this. This is where we explain the final black hole. Okay. Now we do what we were suggesting. We take this part over here, fit it to an exponentially down sinusoid. Okay, it's very simple. There's no trick. The thing is, whenever you ask somebody, can you go and do that? The person will come back after a few seconds and say, "Oh, yes, but where do I start? Where do I start to fit?" And you say, well, you can't do it here because there's two black holes. You shouldn't be doing it there. Just go and do something. That's not like it. They went and did something. That means they took the peak of the waveform and they start 1 millisecond after the peak of the waveform. That's the green line over here. Then they go 3 milliseconds, the purple, 5 milliseconds red, and so on and so forth. Okay? And if they start playing this game very early, you see, it doesn't look good. They're still probably eating up a part of the spiral of this stuff, so it's not good. But as they go later and later, it's wonderful. Okay? It includes all the way from estimate. Sure, the errors are going large because you see, you get an exponentially smaller signal to noise ratio as you move forwards in time. Okay?
So I always get confused with this alien in I don't know how. So this case, for example, is for a very specific. How do you pick up like for which models that be in principle is even in an earlier slide there was some about K, right? So K's are probably alien and
Yeah.
decide that what should be that those here. Like,
So this guy, you should think always about the hydrogen atom because it's a perfect guy. We have L and M that gives us the angular and azimuthal distribution, and then there's an overtone index, and especially when you break the generality that gives you the energy states. Vacuums are exactly the same. We know from simulations that there's one mode. This guy over here, L equals 2, N equals 2, that should dominate the signal, but it's not the only one. We expect to see higher order modes. Okay? So what we do is, well, we take what we're given and we measure the mode which is dominating at some frequency band. We have no way of excluding the other ones.
like are the ratios, no, and the amplitude ratios are between the same measure. The most dominant mode.
Very good point. Yes, very good point. The frequencies only depend on the final state, on the final one, right? Because two parameters, you need to know everything. The relative amplitudes of between L equals 2 and L equals 3, that depends on what gave rise to the vacuums. For instance, it will depend on the mass ratio that you're using to guard vacuums. If they are equal mass, L equals 3 by symmetry is not there. And we were so lucky that the first event is nearly an equal mass event. That's how lucky we are. Okay? But if the merger is not even quasi-circular, if you do some eccentric motion, then you're going to excite L equals 3 to some other amplitude and other modes. That's a very good point. But you see, we always go back to this stuff. Trying to play this game is exponentially hard because we're in the state we wish, doing linearized fluctuations at late times. But that's when we have an exponentially small signal to noise ratio. This was now 5 or 10 years from now, signal to noise ratio will not be 7. It will be of order 40. And when you redo that plot, you're going to find that mode that has such a huge error. It's going to look like this. We will see this autopolar values throughout.
Right. Your previous slide, you were talking about this starting point, like where the linear perturbation is getting pulse. But there has been this two different groups, right? So the Max's group and the Gravitational. So if you keep on adding all these overtones, you might be able to fit it from say 0.
Yeah.
So what's your take on
Yeah.
this?
So one group is my group.
Yeah.
So I would like not to come too much on that, but I think what we understood is that first of all, I wouldn't want to spend too much time on that, but let me tell you an unfortunate thing about modes. It's this plot. So if you see the higher overtones have lower frequency, lower real part. Okay? This is unfortunate to some extent. And they're highly damped. Okay, if you look at these guys, they go up. Imagine one looks very big, okay? So if you calculate n equals 5 or 6, the probability factor is way smaller than 1. This means in a quarter of a period, usually much less, there's no mode. Okay? So you know what Fermi said, right? With 4 points, you fit an elephant, with 5, you make the trunk move. that's exactly what's going to happen with overtones. If you start playing with too many overtones, you can put an entire sound of elephants moving around.
But then it's just fun. If you increase the number of, if you just like if you do parameters.
Yeah, you can always feed in whatever you want, and you're not doing necessarily physics. In fact, there's some evidence you're not doing physics. But that's, I think the two groups agree to a good extent now. There's a review coming, I don't know, in a month or so. This is all going to be beautiful. Either that or kill each other. This is not safe. But so the important thing is that the rain part goes up. Okay? This looks like nothing interesting, but we're trying to fit, you will need backwards in time. No one has the frequency. It's lower. So naturally, this cross correlation that you're doing, this match filter wants to eat stuff. Oh, give me something low frequency, I will use it. You're not necessarily doing physics. Whatever low frequency you put there, the match filter will want that.
Yeah, my question was more about like where is this ideal definition of?
There is none. That's a very good point. The entire point is there is none. There is no starting of ring down. There's never an instant where the signal is an exact exponentially decaying sinusoid. Okay? So if I sit anywhere in space and I look at a signal from a black hole, I will always get a ground component that's initial data dependent. I will always get a right scatter component that came from far away, just we call this tail. And I will also always get something from the light ring, which we call ring down. So there's never, we're trying to do physics, we're trying to dig up all the details of the waveform, but there's limits to it. The full thing is vastly more complex than just separating it like this.
But we are just having like more comments if when we have more like a station which have more events with higher SNR, should that resolve it?
That's for sure. When you have more events with more SNR, I think you're going to certainly see the first overtone, perhaps the second. And when you do that, then you bring down the mass and string, you're running right around the Well, we know that given, that's a good point. We know that given dynamic we see it, but we don't need to do that. We can do exactly what's here. We can sweep across, if you have a single coefficient of thousands, then at least we see. You start at zero, you estimate the amplitude of fundamental mode first overtone second. If you're doing things correctly, they should roughly have most of them. We will know how to do this game, but I think we're not far from having a very robust picture of that. You're really trying to pin me down, huh? Okay, good. We even started going beyond the linearized description. This was just linear. We dropped all the second and higher quantities. Okay. We're now going nonlinear. We're expanding the field equations to higher order to understand what's the nonlinear content in the ring down. We found nonlinear modes that have small amplitude by small in ratio of the nonlinearities to the square of the linear guys is small. It's not technically small. Lisa will see at least a couple of events with this. We will see nonlinear structure that comes from field equations. I think I still have a few minutes. You need to leave in 5 minutes. So let me tell you about how we go around and test whether these are. So how do we do this? The traditional way, of course, the one that we've been using for 3 or 4 decades, is to say, well, I look at the waveform, okay. The objects have to be very massive, 30 solar masses. You look at the waveform, it's a 5-minute exercise to know that the object has to be contained within 500 kilometers. We know nothing other than a black hole that fits this picture. Okay, that's the traditional way. I want to argue that this is a very poor way for a community, our community, that built a $2 billion instrument. Okay, it's a very non-physics way of deciding something. On top of that, the real open problem of physics lies inside black holes. We have no idea how to describe the interior of a black hole. And this means that if you take yourself with a bunch of parameters inside of a black hole, you will not be able to predict the future. How weird is that? Okay. So of course, physics goes berserk in black interiors. So there's a question: do they exist there? How do we know that horizons are created in space? How do we know that? How do we take a gravitational wave and convince ourselves that we're looking at black holes?
Really, I think that equation, what I'm saying, because I don't know whether the space time is no be or not.
That's true. So there is no way, that's the first point. There is no way that from the exterior we will ever be able to show that horizons are present. Okay? This is kind of by definition of black holes, by definition of horizons, whether you want it to be apparent or it's not horizons. There is no way. So the best we can do, well, is to assume that they are not black holes, try to see what happens. Okay? There's a bunch of ways where the non-black hole nature would show up. For example, if you take two spiraling objects, compact objects, one will tidally distort the other, one will create some moments on the other, and this will affect the gravitational effects. Okay? If you look at the final state, the ringing of these objects, of course, depend on their structure. Okay? So if you don't have horizons, or if you have something else, all the ring dancing, the spectroscopy game will change in some way. For example, we can look at tidal effects. It's a magic property of general relativity that when you place an object close to a black hole, like you do a moon close to the Earth, the moon raises tides on the Earth. Okay? It so happens that nothing raises tides on black holes. That raises gravitational tides on black holes. The tidal numbers of black holes vanish. Okay? So you can use this property to go and test whether or not we're talking about black holes. Here's an example done by the Princeton group. Okay? You take, I think in this case, the 6 past events, you try to estimate the tidal number, the lambda, of the objects that are there. They are dominated by posterior at small numbers. They are all consistent with 0. Okay? By the way, the tidal of numbers for neutron stars will be somewhere out here. These are certainly not stars. Okay? This is using the spiral. Of course, we can do this thing using spectroscopy. And here's the first lesson I think we learned. We all thought, well, I don't know if we all thought, many of us thought that the modes that Vishweshvar and Chandrasekhar studied were actually horizon modes. The argument was really simple. Because these frequencies depend on the boundary conditions, surely they must depend on whether there's an horizon. It's a very simple argument, okay? Of course, it cannot be true. It cannot be true because the horizon is infinitely far away in time for any detective to care about. So the idea is simple, right? Well, let's take a star, go right into the black hole. That's my red dot over here. If it's a black hole, you will see the following. Once the star crosses the light ring, there's your effective potential. It excites these waves, these characteristic frequencies of the modes. See it in the gravitational signal. Okay, see the burst? When this burst is created, it travels outwards to your detectors. There's another burst that travels inwards. We don't see it because it's a black hole. It's for animals. Okay? But if it's not a black hole, well, it needs to interact with whatever is there, and it has to come back. Okay? So if it's not a black hole, you should be seeing things like this. The main burst, the things that black holes know, followed by echoes of the original signal. Okay? It's a very, very simple prediction. It's a very robust prediction we learned in the last few years. Anything that looks like a black hole but doesn't have an horizon should ring down at late times in this way. Front ring down. Yes. Yes.
Jump.
Yes.
Do you want to see this?
That's a very good argument. This picture only holds if there's no matter within a relaxation distance of the light ring. This picture only works if your objects really look like black holes. way down to close to the horizon.
Black holes will be because everything else will be.
No. In fact, there are non-linear simulations of compact objects that show this. Okay? They're called black shells by the Princeton group. They are so compact that when they merge, the light ring is in vacuum, is evolving in vacuum. Okay? You're talking about neutron stars, anything. Neutron stars have compactness such that the surface is outside the scope. They don't even care about light rings. Okay? Because,
If you have a black hole and a neutron star merging to give us that.
yeah.
Again, you won't be able, probably won't be able to. Because too much matter.
Well, it depends on the size of the black hole. If the black hole is too large, it just swallows into the neutron star wall. It doesn't even care about the neutron star. That's not the physics I'm talking about. I'm talking about physics that gives structure very close to the horizon. It's not a neutron star. Neutron star is not up in this way. Neutron stars are too easy. We know what to deal with them. Okay, they are just not what I want.
Then you have to understand that this is an observer.
This is an observable.
And I mean, the arguments became.
Yeah.
Seem to tell me that this is observable only when you're looking at two black holes going to a black.
No.
Otherwise, there's too much matter out.
No. As I said, there are simulations. As I said, there are non-linear simulations that show this picture for objects which are not black holes. There's no horizon in the space-time anywhere. Okay?
And including the matter that is.
Including, of course, the matter. Otherwise, we couldn't do that. This will happen. I can quantify this statement. If the surface of your object is close to the horizon, such that on the relaxation time scale, on this time scale, it doesn't interact with matter, okay, then this needs to happen. This tells you that the surface, this only happens if the surface lies within 1.01 Schwarzschild radii of the spacetime. So neutron stars are not in this picture. Neutron stars are too easy. We know what to do that kind. Spectroscopy for neutron stars is understood for decades. That's not the issue. They will never show this. Okay? This is for weird stuff. Having fireballs in your spacetime or somehow doing subquantum physics at the horizon. It's not for kind of well-established normal matter whose surface is at the east or even farther. Neutron stars are compactness of very small things. Okay? Now, this sort of echoes is exactly what dolphins use to see objects. So if they can do it, my point is we can surely do it. And Lino Virgo started doing these searches. Okay? But of course, these searches will always exclude just a region of perimeter space. In particular, they will exclude certain time delay in the region between atoms. But we can do it. And as the detector sensitivity goes up, we are going to be doing what particle accelerators do. You increase center of mass energy, you probe smaller scales, our detectors will become better. That means we're going to probe larger time delays and smaller equal amplitudes of sound.
Echo time is the function of the mass, or like, is it? If you're
The echo time, that's a very good point, is kind of a universal quantity. It only depends on the mass of your object and where the structure is. Okay? Right?
So that means it's stackable.
It's stackable. Unless, of course, you start saying, oh, but the subquantum physics could occur at any thing for anyone. Yes, it's stackable. And I think that's what some of these groups, including Lino, I think are stacking the events together. Okay, do I have 2 minutes? Yeah. Okay. I have 2 minutes, so I'd like to very, very quickly tell you about how we do this for dark matter or for matter out there. I'm trying to talk about vacuum. We're certainly not in vacuum, or I wouldn't be here. So there's no curve bottom, unfortunately. Curve bottoms are fiction. There's matter out there. To which level matter is relevant? Okay, this is a big thing. Or how can we use black holes to actually understand environments? And I postulate that the next 20, 30 years should all be dedicated by this. And I think all major groups in Europe certainly are going this way. Now, when you start placing black holes in matter, let me go back to this picture. Take this binary, it's evolving in some environment, and you see what's going to happen, right? Some of them will start accreting matter, but when it moves through a medium, a new thing occurs. Pass nearby stars, I give some of my energy to these stars, so I slow down. Okay? So dynamical friction, we know more or less how to handle it at the Newtonian level, and you can use this to predict how much faster each spiral is going to occur. See, now each spiral is driven not only by gravitational radiation, but also by dynamical friction and accretion. If you do this for the first few events, or try to predict what happens in the future, you will see that LIGO, for instance, is able to constrain. These are densities. I don't think you can see it, but these are densities in unit of the density of water. And yeah, don't ask me why. It's I just felt like water was good. Okay. The first event, if you look at the spiral stage, the first event tells you that if these guys were spiraling in some medium, the density had to be smaller than 1,000 times that of water. And you say, yeah, right, what's the point? We don't know, we know no scenario where anyway that will occur. Okay? And that's true, but these spirals are just really short-lived. Okay? If you start going to more and more interesting detectors, for example, LISA, if you see extreme mass ratio systems, supermassive black holes, and small guys in spiral, it will be into clustering densities of the order of 10 to the minus 12 delta. So you're doing accretion disk physics. Okay? And if you dream that something like this cycle is going online, and if dark matter spikes do exist, you could even constrain dark matter densities out there in the universe just following these two guys. Okay? We're still at a very, very primitive stage where we think about Newtonian quantities like dynamic friction and whatnot. We need to do much better, but we'll get there. If we're lucky that dark matter actually comes under the form of very light fields, very light bosonic fields, okay? Something with Compton wavelength that could be kilometers or millions of kilometers, then another interesting phenomenon occurs. It's driven Penrose's mechanism of extracting energy. And that's the following. You take an ultralight field, also a spinning black hole, it gets amplified in the ergoregion, it extracts energy, but it's massive, so it can't just go to infinity. It's stuck to the black hole exterior, and it creates clouds. Condensates where the rotational energy of the black hole is accumulated. Okay? Let me show you a simulation showing this. This is what happens when you evolve a neutral light field close to a black hole. I even put some companion over here. It's here. Okay? It's a very generic effect. But you see, it's a non-axisymmetric thing. It's emitting gravitational waves. So you can use these waves to actually show whether the fields exist or not. So we can do particle physics with supermassive black holes. It's a beautiful thing. Okay? I'm not doing this. Let me finalize with the constraints that we have. Particle physics using gravitational wave theory. Okay? This is the stuff we can do. We're constraining right now with LIGO, okay, the existence of new particles with masses of order 10 to minus 12 electron volt. Why? This gives us Compton wavelengths of the order 10 to the square, 10 to the cubed kilometers. When LISA goes into space, then it's going to constrain things of order 10 to minus 17, 10 to minus 18 electron volts, because LISA sees huge wires. Okay? Very good. I would like to finish by going back to where I started. Okay. This is GR at its best. We started with Mitchell, that understood earthquakes and volcanoes, and understood black holes. We built detectors to actually go after black holes. We saw, well, we have very good evidence they are black holes. We have very good evidence that we're seeing gravitational waves, and we're now going to full circle. We detect waves that travel at the speed of light when masses move. Okay? If you think about the interior of our planet, sometimes masses move there. We call this earthquakes, right? And the traditional way to actually catch an earthquake, well, is to detect a seismic wave. But seismic waves travel at a few thousand kilometers per second. Gravitational waves travel at the speed of light. So the idea in the next few years, I hope, is to actually use all this technology to detect motion inside our planet using speed of light physics. So we're going to be able to prevent thousands of deaths, probably, because we're going to have up to a minute early warning gain. Okay? So it's, I think, a beautiful full circle thing where you even find applications that save lives for yourself through the physics. Okay, so I'm going to finish by saying it's a wonderful new era, and it's easy to say the things we're going to do in the future, but it's also very challenging to find precise new ways to quantify how we're going to constrain GR to the next sensible place. And I think that's work to all of us. So thank you. Yes.
Yeah. So I will go back to my stacking question for this element mode. So what will show that if and tau for them sort of interesting motion for black holes which are not spinning, but when they are spinning, and like you have all these element modes, is there a way to construct a quantity which and we are looking for a single quantity to see whether no gain field is valid or not.
I don't know if that's single quantity, but I think the procedure is equivalent to what you're saying, right? Because we still have only zero freedom. For any event, if it belongs to the Kerr family, we have zero freedom. No mass and spin, that's it. We have the frequencies only depend we even have a functional form that's accurate to within 0.1%, right? So we have an expression that tells you tau, the time scale and the frequency, as a function of mass and spin. So you can certainly stack these events, of course, maximizing the mass and spin that fit this.
Yeah, what I was saying is that without getting element.
Yes, you want to renormalize the things such that there is a. I don't know of that. I don't know. I don't think that was done. It's a good question. I don't think that this normalization to a single quantity was done. Yes, that's a very good. That's worth thinking about. Maybe there is something. Any other? Yeah.
So, talking about your strike on technicals, is there a particular smoking run which can say that this is definitely an echo, but not an environment because you know, like if there is a bosonic field,
Yeah,
it is not give you this secondary box.
that's a very good question. So to be honest, I mean, if you start seeing something like an echo, like this echo, or you see evidence for a non-zero tidal number, I will be delirious for a week, and then I would think, okay, wait a minute, maybe these are environments. Okay, now the aspect of any fundamental theory, okay, is that it's fundamental. That means there should be a new fundamental scale in the problem. For instance, where exactly is setting this time scale? It must be a new fundamental parameter. Okay? And if it's a new fundamental parameter, it can't depend on environments. It's fundamental. So if I look out there, I need to find the same thing that I'm going to find there. Astrophysical environments, they're all over the place. What I'm trying to say is, I don't think with a single event you can detect new physics, which I would argue the case for whoever's doing beyond GR stuff. Please first work out the dirty business. Okay, but so I don't think that with a single event you can detect new physics, but when you start gathering lots of events, then it's easy to see where environments are and where you're zoning in a new fundamental scale.
Because it's always one of the biggest problem for all of us is when we find something new, we have to go through a lot of changes.
Of course.
We don't know whether it's
I understand. Of course, and the same thing with these bosons, right? Boson, if it's a fundamental field, it has a very precise scale, 10 to minus 12. Okay. So if you look at all black holes out there, they all should be pointing to 10 to minus 12 and 1 to 4. Environments will be all over the place. Yeah. I mean, it's tough work, but it's beautiful work. We need to reach the stage where we actually see something that doesn't belong there.
Amazing mentioned like on the stacking part, some people are doing that stacking. So it is
What they do is they get the studios on say the power.
Oh,
Self postpone the.
I guess.
yeah, so this plot about the QNA versus frequency indication. So depending upon where exactly you start is
Yeah, you mean the spectroscopy, this one?
yeah, this one. So do you understand why this movement is towards a lower QNA frequency?
You mean here?
Yeah, start.
I mean, it's not too unexpected, right? Because if you look at this thing, anywhere you start feeling, if you start going to the left, it's in spiral, right? It's a chirp. Whenever you go to the left, you will find lower frequencies. I mean, I don't think there's any escape out of that. If, okay, outside of this, now going back to the overtone question, if by chance your spectrum was such that higher overtones at higher frequency, I very much doubt that we would be leaning to think, oh, there's higher overtones. They wouldn't belong there. The overfitting was useless. But so I think here it's really just because it's lower frequency.
It's just taking the
Yeah, it's just taking, I need lower frequency. I'm going to use whatever lower frequency I can.
then the decay calculation still is fine, which is not very much.
That is true.
Ideally, you
Yeah, that is true. Although, error bars are still very large. Yeah.
raise the question on Zoom. The Zoom there is a question. Pranjal, you ask the question.
There it is. How do I do that?
How is it going there?
I should be unmuting, no?
Sorry, that
This is the divine. Somebody's there. So. This is how do you scroll on this? Post has to allow.
Yeah, but I cannot scroll it up. Okay, got it.
Oh, there's that.
There is there. Okay. Pranjal can.
No, but it's still muted.
Okay, I think.
Yeah.
Hello, can you hear me now?
Yes, perfect.
Thank you. Yeah. Pranjal Trivedi from Hamburg Observatory. Thank you, Vitor. Again, as always, excellent and inspiring talk. My question is about quantum gravity. Can black hole spectroscopy and ring down analysis in the LISA era, as you kind of indicated, get us to the level where we can probe some hints of the quantum gravity microstates of the horizons to shed light on the nature of quantum gravity, and what are the promising ideas in this direction?
Thank you, and thank you for the kind words. I have just two things to say about quantum gravity. The first is we have no theory of quantum gravity. Yes, from suffer. Second is we probably don't know where quantum gravity lies. I think, as usual, physics is about measurements, so we need to collect data and see if we find new things. Having said this, if quantum gravity, so there's a few ideas in the air. One of them relates to these scales over here. If there's structure at the horizon, okay, there's a nice property of these geometries. And even if you place the structure at Planckian scales, okay, these time delays are still of the order seconds or smaller. No. If in some sense you think of that as doing quantum gravity, then we will access that. Okay? But I also think it's a bit naive to think that the Planck scale or that the Planck constant has necessarily anything to do with quantum gravity. It could come at probably any scale, and there's been, well, some clues for that in the last decade or two. So I think we should keep an agnostic view. There was an attempt by Bekenstein many years ago at quantizing the area of black holes. And surprisingly enough, even that is governed by the Planck constant, and that is going to give us physics like that in this slide. Quantizing the area of black holes in the way that Bekenstein tried to argue would still lead to something that looks like echoes with time scales of order seconds or less. So we could be seeing that. I think we're becoming quite good at doing this sort of post-merger signals. I hope this answers more or less the question, at least the fragment. Okay, the last question.
Yes. Say that we in the current and current 10 years solution of other MOSFET ways. So how are we doing out the other ways of it, or are they very specific?
There are good. So the question is, we are thinking about curve and general relativity. How do we test all the theories? And the idea is more or less simple. The idea is in GR, the modes, for instance, depend on two parameters. If you start going to a new theory with some new scale, there will be three. Okay. But that means, again, going to the stacking, you can still start, you either look at two modes, so you test the theory, or you start stacking events to actually constrain the new scale. This has been done for one theory, which is the theory that expands Einstein's equations in higher order powers of curvature. I think it's a very well motivated theory, and not because the work is mine. Okay, but this sort of game can be done. It's more challenging because you see, general relativity, we know it's a well posed initial value problem. We know how to take initial data and predict the future. Most of the theories out there, the equations of motion are higher order. So even placing them in a computer faces huge challenges. So I can do spectroscopy because it's relatively simple, but evolving these guys at large distances is still a big challenge. Oh, ah,
Thank you.